Thank you for joining in person or remotely. My name is Slattery, and I'm a fourth-year PhD candidate in the Energy Graduate Group. And the theme of my presentation today is if every time somebody asks me what happens to the batteries when I tell them what my PhD is about, if I had 15 minutes and the support of PowerPoint slides, then this is sort of what I would say. So I'm hoping that this should not require much background knowledge, but if I'm losing anyone, please let me know. And I'm going to talk about basically what I've learned over the past few years, researching talking to the people who would be involved in battery or vehicle life end of management, and then also the work that I've done with Jessica Dunn and Alyssa Kendall in informing policy recommendations through California's AB 2032. The motivation for this is that when I was in this room as a first year master's student, and I was learning about all the exciting progress California is making towards decarbonizing our energy and transportation systems, I was very struck by the central role of batteries, both for electrifying transportation as well as storing energy from intermittent renewables. However, I'm also a product of my generation, and that means that I saw WALL-E when I was in 9th grade, and it was a very impactful film in my life. And I also am very acutely aware that batteries degrade over time and are often a limiting factor for technologies. So I was kind of curious what the plan was for the batteries at end of life. And at the time, I think even just since I've started looking at this in 2018, I think there's been way more attention and progress made on this. But at the time, there wasn't really a satisfying answer. So, and also something else that I learned as I was learning about this was that a lot of research focused on how many batteries would be retiring at end of life, or what recycling technology existed, or how much capacity there could be for repurposed batteries. But there wasn't a lot of understanding on how the batteries would actually get to that point, and who was collecting them, where the vehicles would be at end of life, and kind of what was needed to make sure that they would get to the doors of a recycling facility, for example. So my research attempting to answer that question has relied a lot on semi-structured interviews. So I've talked to people who are auto dismantlers, battery recycling companies, battery repurposing companies, auto auctions, parts dealerships, battery aggregators, and just generally anybody who would self-identify as being somebody who's going to handle the electric vehicle at some point. And in these conversations, I kind of just talk about what their operations are, what they do, how they acquire vehicles or batteries today, their process, and then what the outputs of their process are. And I also ask them how they expect things to change when more vehicles on the road are electric, where they see areas of opportunity and where they see challenges or what the concerns are. And then in parallel, as I mentioned earlier, I've been part of a team that was providing research support to an advisory group that was convened by Assembly Bill 2832 in California. And the purpose of that advisory group was to give recommendations to the legislature about what policies might be needed to ensure that as close to 100% as possible of electric vehicle batteries in the state are reused or recycled at end of life. So that was taking place from 2020. We had one meeting in person, and then something around March 2020, something happened and everything went online. But we actually just wrapped up that process. And as part of that process, we facilitated smaller discussions about specific aspects of end of life. I've had a lot of really great input from the advisory group and other stakeholders to identify barriers to reuse and recycling today, and then brainstorm solutions. So for this presentation, mainly what I'll talk about is trying to really quickly give an overview of what's happening to electric vehicle batteries at end of life and sort of the current status of the reuse and recycling industries. And then I will quickly talk about what the policy recommendations are, but this is all going to be very broad, and I welcome any questions about it. So generally, in academic research at least, it's often assumed that when an electric vehicle battery reaches end of life, it will be returned to the dealership where the car was purchased. However, in reality, that's just one of many possible pathways. And because it's largely unregulated at the moment, and if you've purchased a vehicle, then what you do with the vehicle and the battery is kind of up to the consumer. So actually, the pathway depends on the reasons for retirement, and it could end up, if it's in an accident, it could go to a salvage auction. It becomes the property of the insurance company and then is sold at an auction to a licensed bidder, which could be a repair shop, a dismantler, a dealership, or a variety of other businesses. And there's a lot of just kind of DIY. Well, when I say a lot, we don't know how much this is happening, but to some degree, there's kind of a DIY repurposing world out there, and you can buy batteries on Craigslist. You can go on Reddit and get like feedback on people who have repurposed electric vehicle batteries for their own off-grid applications. You can go on YouTube Watch. It's really dangerous, and please don't do it because they're extremely high voltage and require a lot of safety precautions. But the purpose is that there are a variety of pathways that they could take in reality. And there's a lot of industries for like scrap metal recycling and auto dismantling that will also be impacted by this. So this is kind of the flow chart that I have, like preliminary flow chart that I have put together based on my conversations. And I actually don't think that I have time to walk through all of it. So the takeaway I think that's really important to keep in mind is that they could end up in a variety of locations depending on the reasons for retirement. For example, if the car was in an accident, and in that case, the car's at the end of its life potentially, but the battery might not be. Or if the battery no longer is performing acceptably, in which case the battery might be at end of life for not. Something that I think has been really interesting learning about this is that a dismantler who would probably acquire a vehicle at an auction if it became the property of an insurance company, their business model at the moment is reliant on having a lot of different parts that they remove from the vehicle and then resell. And so as cars become electrified, a lot of those parts of the engine are just being replaced by the single battery. And their business model is kind of increasingly going to be dependent on the batteries having residual value at end of life, and on the dismantlers having the capacity to disassemble a high voltage battery, which is a much different process than taking apart an engine. Also, interestingly, scrap metal recyclers have voiced kind of a similar concern about the impact of their industry, because electric vehicles have to be lightweighted in order to have a good range from the battery. So that means potentially less aluminum and steel and metals that have been kind of the bread and butter of that industry for a long time, and more like carbon fiber and composite metals and metals that are more difficult to recycle. Another challenge that people have mentioned are both transportation and storage. So transporting a battery can be a significant part of the cost overall of end-of-life processing, because they're very heavy and they also have to be packaged a certain way because they're regulated as a hazardous material. And then another issue is storage. So for smaller operations that don't necessarily know what to do or have an immediate off-taker for a battery, they don't want to be holding on to them because they have to also follow fire safety protocol and they take up part. And that's kind of also reflected in the barriers of the subcommittees for reverse logistics. Reverse logistics referring to the process of handling and shipping the batteries identified in our discussions. So the challenge of capturing out of warranty batteries because we're not sure where they're going to be or if that party has the resources necessary to handle them. and then storing batteries, transporting batteries, and especially transporting damaged batteries. And then another barrier was the information that's needed to make the best decision about where to send the battery. It's necessary to know what the remaining capacity of the battery might be, and that's very difficult, particularly if it's already been removed from the vehicle. Wow, I need to really speed this up. So reuse and repurposing, I think, is a bit more of a familiar topic, probably at least for people in this room, because we have a repurposing startup company that was started right out of our energy graduate group. But the basic premise of reuse of a battery is that there could still be remaining capacity in the battery, either to be used in another vehicle if it was retired because of an accident, for example, or to be reused as stationary storage. At the moment, there are several repurposing startups in California and elsewhere in the United States, as well as globally. And the California Energy Commission has done a lot of concerted effort to fund research and demonstration projects to get data on their performance. This is an example of a utility scale repurposed battery storage installation. And here you can see these are modules that have been removed from a vehicle, and then actually I think they repurpose the entire pack. So they remove the pack from the vehicle, test it, and then it has to be reconfigured so that the energy output is going to be kind of consistent across the packs, and it will perform on the stationary storage. Some of the barriers that were identified for reuse and repurposing, one is that they have to compete with new battery systems, and the cost and price of new battery systems is falling. Well, for a while it was falling. I think now with the supply chain issues, there's more concern about the costs raising for battery materials and battery packs. But for a while, those costs were pretty steadily decreasing. And meanwhile, a repurposed battery system, you have to test the batteries to some capacity. You need to reconfigure them and repackage them. And you also need to provide a warranty that will make people feel confident in the performance compared to a new system. So that was one barrier, which I think the CEC is addressing pretty effectively with their research available. Some other barriers were that in order to get connected to the electric grid, the process of repurposing the battery needs to be certified and go through industry certification standards, which requires a lot of resources. So that's a barrier for smaller companies that are hoping to enter the space. There's also the transfer of liability and ownership is kind of, I think, also a solvable challenge, but essentially it needs to be really clear that if an electric vehicle battery is repurposed, that it's now the repurposing company who owns and is responsible for that battery. And if there's a fire or some sort of safety incident, that they are now the ones liable and not the auto. And then finally, there's a similar issue of the lack of access to information that was identified by the subcommittee. So again, it's difficult to access data about the battery once it's removed from the vehicle, and if each battery has to be tested, that's just adds cost to repurposing and makes the process less efficient. And then additionally, there's the repurposed battery installations have to use the same type of battery, and pretty much all of the makes and models of electric vehicles have a slightly different battery pack composition. And so that also complicates things. Okay, next is recycling. The main thing that I want to convey to this slide, and that I also stress when people ask me about this, is that I think people expect that this is going to be a very bleak situation and that the batteries are not going to get recycled and that nothing's happening. And in reality, there's actually quite a few companies that have either operational or planned recycling facilities in the US and Canada. So that's mainly what this slide is meant to convey. And each recycling company has a different process that they're working on, but the general gist of it is that they get the battery pack, it goes through a pre-treatment process, which involves sorting the batteries into similar chemistries. I think not everyone does that, but it makes it more efficient. And then some sort of shredding and separation so that you get the metals like copper, aluminum, plastics, and iron that are processed in their way. And then there's something called black mass, which is usually a composition of the cathode and the anode materials. And that's important because that's where the cobalt, lithium, nickel, graphite, kind of some of the metals of higher value and more concern are going to be contained in that. And then in order to then be used as inputs into battery production, they have to go through an additional metal refining process and then into a cathode production and then cell production. So that was very fast. And if anybody has more specific questions about that, please let me know. Some of the barriers that the subcommittee identified to recycling in the US today, one is, as I mentioned, that output of most recycling processes has to go through an additional refining step and production into battery capacity. And at the moment, we don't really have the metal refining or the cell production here. So even if those batteries get recycled here, they would then have to be exported to be turned into battery inputs somewhere else. And that makes it, first of all, more expensive, less environmentally friendly. You don't have the same strategic advantage of retaining control of critical minerals. And it also makes the market more difficult for them to access. Redwood Materials, as I borrowed their graphic for this, I think they're doing their own, they have their own on-site refining process that they're optimizing their recycling for. But other than that, it's pretty much going to have to get exported. Another barrier is that as battery technology develops, they're innovating different cathode chemistries. And so batteries today have a lower cobalt content than batteries did 5 years ago. And they're hoping to continue that trend in the future too, because cobalt is a high cost and kind of problematic metal. But cobalt is also the most high cost metal. And so it makes it the most valuable output of the recycling process. So as the material composition of the batteries changes, the profitability of recycling changes, and that just makes the economics kind of insane. And then finally, for a closed loop, meaning that the recycled products get reused in batteries, there just needs to be more. Oh. Oh, there you go. Batteries. Okay. Given all of that, some of the policy recommendations that came out of this process, the really big one was that it's really important to define a responsible party for who is going to pay for collection and processing of recycling, assuming that it's not profitable, and especially given that these batteries could be ending up in a variety of different places and are hard to track. And then the other policies were kind of oriented more towards removing the more specific barriers and generally making the whole process more efficient. Gosh, things are getting really chaotic in here. To increase access to information, we recommended that batteries have a physical label that identifies information like what the cathode chemistry is, as well as a QR code where people could scan it and get more information about how to disassemble the battery and other details like that. They also recommended having targeted incentives for recycling facilities and a guaranteed permitting timeline in California, because the permitting timeline apparently at the moment is just really long. And it seems like at the moment, having recycling in California is kind of a non-starter for the industry. I'm out of time. So I will just, actually, if anybody wants more details on what the policy is defining responsibility, poor, then
Fine, Meg.
yeah. So those recommendations have been submitted to the legislature, and there were a variety of implementation and details that would need to be worked out for all of them. Some of them would definitely require legislation. Some of them are more recommendations for agencies. CARB already has a regulation in process requiring labeling, for example. So what happens next is kind of, they're sort of out there for anybody to take them and run with them. I'm still wrapping up my stakeholder interviews. So if anyone knows someone who works with end-of-life batteries or is tuning in on Zoom, please, and you'd like me to ask you a lot of questions about your opinion, let me know. I potentially might develop a survey following the interviews to be able to get a sense of the quantity and volume of batteries that are going to these different channels. Because right now I kind of have it mapped out, but I don't think anyone else can say with any confidence what percentage of batteries are going to a dismantler versus a dealership versus whatever else. And yeah, at the end of this, I'm hoping to have a white paper and a journal article that's kind of mapping out the ecosystem and then making recommendations for how researchers can more accurately represent end-of-life pathways when they're predicting how much material will be available for recycling or analyzing the effects. This is a meme that I made when I was having fun making this presentation. And that is the end of my chat.
Good job. All right, any questions in the room or online? If you're online, feel free to chat and I will read your question out loud.
Fabian.
Great talk. I think it's really, I don't know if it's as much of a question, but I think it's a really good idea doing the QR code and counting of cathode material because I know there's just exposure through LCA work that I've been doing with Jess. It's just like the difference in chemistry of cathode can help guide in the recycling process how much you're supposed to get out in this precious metal. So it kind of helps standardize, or it could help standardize, you know, like, oh, we're missing some cobalt, like we need to refine our process and whatnot because we know this is our starting material. So I think that's a really good input, especially the QR code and the tag actually defining the chemistry.
Yeah, because I think, and with that, it's sort of reliant on people just having the experience of different processes require the recyclers to sort the batteries to different levels. But a lot of it also has to do with the economics of you want to know how much of each metal you're going to get out so that you can tailor the process accordingly and kind of make it the most efficient. And right now, I think sometimes people just have to, they've been working with batteries for a long time. They kind of know like, okay, this is a Nissan Leaf battery. The Nissan Leaf battery in this year were mostly lithium manganese oxide, but to make it more, to kind of just remove the barrier. And that was probably the most widely supported policy. Like I don't think anybody was opposed to that. There was some level of like how much detail is shared. The OEM, but the original equipment manufacturers don't want too much detail because it's all super proprietary, but that was a popular recommendation.
Questions? Any questions online? They should put trackers on them. That'd be kind of fun.
Oh, that actually is.
Did that come up?
Yeah, so there's this is being more promoted in Europe, but called a global battery passport. And that would be kind of a similar, like there would be a QR code and then whoever was going to look at the battery would scan it and input information to be able to track it throughout its lifetime.
All right, well, Leslie's presentation is taking over. So,
It is a very large.
is it very
file.
large?
A lot of animation.
Oh boy, watch out, folks.
Yeah.
Stay tuned, it's worth it.
Maybe. Just trying to make it palatable. I don't have it pulled up on my computer, but I have a.
Oh, that's, yeah, I think I have write examples. I can also join as join share, or I can share from my computer because I have to give it a second. I'll get it ready on my computer.
Yeah. It's fine, I don't need like the presentation.
Oh, here's a question that just came in anyway. Is this fragmentation of the supply chain only visible in electric cars, or can it be applied to other technological products like phones, et cetera?
I think you could probably do this with other products as well. And I mean, the recycling and end of life for those is much more well established. So I would imagine you could probably fragment it with more certainty. But I'm not sure if it's.
Is it working?
There it
It is
is.
working right as I got it up. I'm like, oh, there it is. Okay. Should be able to do presenter, and hopefully the clicker works for you.
We'll find out.
We'll find out.
All right, so hi everyone, I'm Leslie, I'm a second year master's student in energy graduate group, graduating in just a couple weeks. And this is my fellowship project from this last year for University of California Office of the President through the Carbon Neutrality Initiative, looking at charting a path to carbon neutrality with cogeneration plans. So before I jump in, I recognize that I studied chemical engineering. I also studied at a different UC, so I love the UCs. I also love power plants, so I know a lot about this. But for everyone in the room, I wanted to poll you on what you know. So first, by a show of hands, did you know that the UC owns natural gas-fired power plants? Yeah, good, about half. Did you know that those power plants sit on the UC campuses? Yeah, very good. This is actually me at UCLA, my undergrad, on the roof of the cogen plant at UCLA. And then also, how many cogen plants do you think there are in the UC system? Mind you, there are 10 UC campuses, there are 5 medical centers, so like 15 hypothetical sites. Does anyone want to guess a number?
It's like 7.
7 is exactly right. So we have got UC Davis Health System in Sacramento, not UC Davis. We've got UCLA. I think that's supposed to be Santa Cruz, San Diego, Berkeley, Irvine, and then UCSF. So today I'm going to talk about those cogeneration plants and the carbon neutrality initiative, my specific fellowship, the campus plans and their transition plans, how to electrify a cogen, and then we'll talk about next steps because this project just wrapped up. So for those of you that don't know what a cogen plant is, it's basically a very efficient natural gas plant. Instead of just taking natural gas and water input and generating electricity, it takes all the waste heat that comes from that combustion process and uses it to make useful materials like high pressure steam that you can then use to heat your campus, send to an absorption chiller to make cold water, send to a heat exchanger to make hot water. So basically they take that turbine that has like 50% efficiency and they use all the heat products to ramp it up to over 80% efficiency at times, depending on the plant. So they provide really low cost electricity, you generate it on site. They're reliable and they're resilient. I mean, it's base load generation for the UCs, and they have a long useful life, they're power plants. So now shifting gears, I'm going to talk about the carbon neutrality initiative. So UC President Janet Napolitano in 2013 announced that the UC would be carbon neutral by 2025. That's for all of our buildings and vehicle fleets, for all the campuses and the 5 medical centers. And you might look at your watch and think, oh my gosh, it's 2022. Are we there yet? So let's see how we're doing. The UC has a clean power program to procure carbon neutral electricity for the campuses. There's been a ton of energy efficiency projects over the last decade. There's also been renewable energy projects on campuses. The largest one here at UC Davis, the 16 megawatt solar farm. And UC is also awarding funding to UC initiated offset projects. These are kind of like research projects that also have like a carbon offset aspect to them. They're pretty cool. And if you look at this graphic, you can see that dotted line is where we would be without the carbon neutrality initiative. It's going up because the campuses have grown over the last decade. But you see that we're ramping down, and isn't that lovely? But you might look right here about 2024, what's gonna happen here? That's like a third of the emissions. Where are they gonna go and where are they from? Those are from our cogen plants. They're the biggest challenge to meeting carbon neutrality. They're currently responsible for 50% of the electricity on the UC and 78% of the emissions. So if we want to get to carbon neutrality, we got to do something. Enter my carbon neutrality fellowship. So the UCOP, Energy and Sustainability Unit, hired me to take this last year to collect a bunch of information about all the different campus systems. This actually applied to the cogens and the central plants. I interviewed the energy managers and the central plant operators. I also did a bunch of data collections, made lots of spreadsheets and bothered people to send them back to me, and they did, which is very nice. I developed energy flow diagrams for each campus and put it all into a massive report. And that report should be used for system analysis, for planning, and for developing policies to see what we're going to do with these plants. So looking at each cogen plant, they're all unique. You can look at UC Santa Cruz has a 4 megawatt plant. UCLA is 40 megawatts. That's a notable difference. The oldest one is UC Berkeley, 1987, approaching its end of useful life in many ways. The newest is UC Santa Cruz, 2015, 2 years after we announced we were going to go carbon neutral. But UC Irvine, this is an example of one of the energy flow diagrams. So I looked at all of the natural gas inputs to the cogen. I looked at how much went to heating and cooling, which is not exactly just the cogen, because I also looked at the chillers that were driven by electricity from the cogen. We also get the pure electricity to campus and the waste heat. UC Irvine does not have very much other gas purchases because pretty much all their buildings are hooked up to this plant. That's not true of every campus. They also have some purchased electricity and some solar generation. Another thing that makes them all unique, they all have different products. So UC Berkeley has electricity and steam. They have a steam heating system. So that's basically their entire campus, electricity and steam from the cogen. If you look at the UC Davis health system, they generate steam, hot water, chilled water. Some of these cogens generate like vacuum air. There's some compressed air that's used for like pneumatic controls. There's cage washes in the hospitals. They provide a lot of interesting utilities that are hard to make in a different way. One thing that's particularly important on each campus is what is their campus heating system? Is it steam or is it hot water? And there's also high temperature hot water, which in many ways is a lot like steam. It's like 350 degree water instead of like 140 to 160 of a hot water system. I know there's a lot of UC Davis folks in the room. We've been doing on our campus a conversion from steam to hot water. It takes years, takes lots of money, ripping out lots of pipes. So each campus is developing their own transition plan. That's how the Carbon Neutrality Initiative works. UCOP said we're going to meet it, and they said each campus make a plan. So what are they thinking of doing for my interviews? One is offsets and credits. Keep running these plants as usual. They generate a lot of electricity and useful services. UC policy, the sustainable practices policy does state that it can't completely be met by credits. Credits are supposed to be kind of a bridge to a solution. They also have some notes that 80% needs to be met by something other than credits. So that can't be the total solution. Another big topic is biogas. Using basically generating methane from wastewater treatment from landfills. And how that works is you generate it usually somewhere else, like maybe Louisiana. And there's a facility there that you're going to generate some biogas, you're going to inject it locally into that place's natural gas system, and then you're going to get credit. And over at the UC, you're going to continue using natural gas as you would have before. Biogas is not a scalable solution.
I was just wondering if, so does that is not considered a credit or an offset?
That's a good question. I guess when we think credits, we just think like charged credit.
Like bought it, yeah.
Whereas UC has made a lot of investment in biogas, so it's often seen differently.
Yeah.
It's a great question, I don't know. But as far as our biogas, it's expensive to procure, although the UC is investing a lot in it. There's limited supply. If we were going to meet the entire UC system demand with biogas, it would take up 3.5% of the US's potential biogas. That's not how much the US has, it's how much it can potentially produce. It's a ton of biogas. This is not showing leadership by the UC if they're just going to use biogas. It's also continued investment in natural gas infrastructure. I talked about how it's generated locally and injected elsewhere. And then also these plants sit on our campuses. They're generating on-site air pollution. I mean, where there's combustion, there's NOx emissions. Where there's NOx, there's often smog. So not a great solution. What else can we do? For some of the campuses that are really tied to having their high heat systems, meaning they really like their high temperature hot water and steam, they talk about things like geothermal, concentrated solar, or hydrogen, but these are not really things that have been done before on a campus. It's not really a plug and play solution. So the last option is electrification, which is my favorite, and it's the one that most of the campuses are saying they're going to do. That's what most of them are planning for. So I'm going to run through this super fast, but here's how to electrify a cogen plant. So first, you've got your turbines that are generating electricity. We're going to get rid of those, right? Because we're not going to generate electricity on site anymore. We're going to purchase it from a utility. But you might have noticed that's where our steam was coming from, the majority of our steam. So we'll talk about that in a second. But next we can look at our chillers. We've got some steam chillers and maybe a couple electric chillers, depends on the campus. Get rid of our steam chillers, maybe add some electric chillers, add more electricity, because that's a lot of incoming electricity, and connect it to those. Now we can also look at our hot water system, if we have one, usually generated from steam as well. So no steam to that. Hopefully our system is designed to a temperature that can accommodate a heat pump. That's not a given, but we could put a heat pump and bring electricity to that. And then lastly, some of our campuses are heated with steam. Maybe we do a big investment in steam to hot water, get more heat pumps, and that's how we would do it, right? This is a terrible example. It's really just to show you how everything's interconnected. There's much better design for these systems that's more integrated. We use heat recovery chillers and thermal energy storage. So like this is not how you would electrify a cogen. But you can see how everything is dependent on this high grade heat that comes off the turbines. So each campus, one of the questions I asked them, which is, what is your biggest barriers to electrification? Number one, capital cost of equipment. You're essentially building a new plant. I just showed you all the equipment you would replace with something else. It's a lot of money, and it needs to come from somewhere, and where's it going to come from? Number two is operating costs. The cogens generate electricity very cheaply. I can't say for certain how much it costs because it depends on what you're factoring into that cost. Do you factor in all the equipment you're replacing every 10 years? That's pretty expensive. But it's not completely unfair to say purchase electricity will cost roughly double. And you're going to purchase a lot more of it if you're electrifying your campus. So operating costs will go up pretty high. Next is space constraints. Thinking about some of our campuses like UCLA, UC Berkeley, UCSF, in the middle of major cities that are already very dense, are they going to be able to find a city block to build a whole new power plant? Also utility service upgrades. So we talked about how much more electricity would need to come to the campus. You have to work with your utility to get those higher grade lines. It takes time, it takes a lot of administrative burden, it's money. And then lastly, our existing heating system design. This is really a kicker. If you've got a high grade heating system, it's really difficult to switch to an electric format. So you might be like, oh my gosh, Leslie, with all of these challenges, can anyone electrify a cogen plant? Can anyone even do this? Yes, Stanford did it in 2015. This has already happened. And they did it with a steam to hot water conversion. They did a lot of great fancy math. They developed their own thermal system. There's heat recovery chillers. They've got hot and cold thermal energy storage. It cost $500 million, which is not bad, depending on your perspective. And it took 5 years from planning to completion. Pretty cool if you're a private university with a lot of capital. It's also beautiful. I took my engagement photos there. I took my engagement photos a lot of places because they were clean energy themed, but doesn't that look nice? So we need near-term solutions for 2025. It's just around the corner. Stanford, it took them 5 years. It's going to take more than 5 years for us. So our near-term solution will likely be biogas. Like I said, UCOP and the UC system is investing a lot in biogas. So they're going to procure it. I think they have contracts to meet 20% of the UC system demand with biogas right now. That's not enough to keep all of our cogens operating. So probably some offsets as well. But then what's next? I spent all year developing this report that has so much information on each campus. It details their systems. It looks at their energy flows. So hopefully they can use that for system analysis, planning, and policies as they stated. Also in the UC Sustainable Practices Policy, every campus needs to have a formal assessment and plan for their Scope 1 emissions, which includes cogens, by 2035 or before they need to do a major equipment replacement. And it needs to be met 80% of those emissions through means other than offsets. So there is a policy in place by 2035, even though we'll be carbon neutral 2025. And that's my presentation. Thank you to UCOP for sponsoring this fellowship, which is very much my passion project. I would have done it for free. And thank you to my supervisor, Eric. And thanks for listening.
Any questions here in the room or online? If you're online, feel free to raise your hand or send it in the chat.
Yeah. I mean, first of all, just like great job. This is a really good presentation and like a super impressive project. So shouts out to you.
Thanks.
Also, I'm wondering what the feedstock is for the biogas plant in Louisiana and why, like, if there's something preventing having a more larger scale biogas plant here in California.
So the one that I showed a picture of is the largest one, and this is in Rialto, which is Southern California.
Oh, okay.
There is one in Louisiana, one in another state in the East Coast, I can't remember. But really what it is, it's not, I mean, this is for a landfill. It's just the capacity of the landfill to generate gas. So there's got to be a lot of purchases. And like I said, the total potential of the US is not that much biogas. But it is pretty cool because there are other harder to decarbonize sectors that I think will benefit from this biogas investment in the long run. So I don't think it's a wash to invest so much in biogas now. But it would be if we invested a lot of biogas and would never to get this.
Yeah, and we're like also kind of starting to try to convert to hot water and stuff that'll make it possible to electrify things eventually.
Yeah, I mean, some of these plants are pretty new, some are older, so it really depends. I mean, you don't want to like abandon infrastructure because it is really valuable infrastructure. So it's all about, in my mind, it's all about having a really thought out, thoughtful plan. Which some campuses do and some are less thought through.
Has anyone tried to hire you to do that yet?
No.
Yeah, I was just wondering, given the different UC campuses are shifted different times, like there are gonna be infrastructure and equipment that are gonna be left behind. But like, can the campuses share easily? Like, let's say one, like UC Davis is moving away from steam and there are like all the steam components. And the campuses like leverage.
Like collaborate on how to do it?
Yeah, collaborate on the stepwise, like, okay, I'll do it right now and then you can use some of this equipment and like, share the infrastructure.
Yeah, in terms of actual sharing physical infrastructure, not as much, because these are like big pieces of equipment, hard to move. A lot of the time they're just decommissioned in place. So I don't know about that as much, but in terms of sharing knowledge, I think there is a good amount of it. I mean, it's a UC system. We all are connected in various ways. A lot of these energy managers know each other and have these reports written. So every campus is unique, but there are some common themes, right? Like the steam campuses can all talk to each other. The hot water campuses can all talk to each other and think about it. Yeah.
All right, well, Bruce Chamberlain sent his good wishes. He said you did a great job and enjoyed working with you.
Thanks, Bruce.
So you said UC Santa Cruz built this cogen plant in 2015 after they were already going zero power emissions. So do you know like why they did it or what the reasoning was? It seems like a big challenge for them right now.
Yeah, it's true. And you know what? Their cogen plant is very small. It's 4 megawatts. And a lot of the reasoning behind it is UC Santa Cruz is located at the end of a residential power line. So they had really unreliable electricity. And their cogen doesn't feed their whole campus. It's really just built to provide electricity for their research labs and their like science and engineering campus. So it was a really intentional, thought out choice to make sure they had reliable electricity for these campus needs. And they designed it, you know, efficiently. They used what's left over for heating. But that's another thing about these cogens is like, one serves a hospital, right? When we want reliable power to a hospital, I mean, they were exporting electricity to the grid during outages in 2020. So the reliability does have a lot of value. It doesn't mean it couldn't be met by something that's not a cogen, like some batteries, some thermal energy storage. Those all cost money and they're investments in infrastructure. So the reliability is a